Um, Good morning again. I just want to make a few announcements. You know that you're going to access everything from class. Just remember that, I have assigned the first homework. Probably you already know about this. You're going to find all the homeworks in the respective chapters. Just keep this in mind. The deadlines will also be ordered. But we are in the second week right now, but the first homework is due. Just keep this in mind, all right? So to do the homeworks, I don't want to write down an extensive way of actually entering data into Stack. So as a result, I just prepared these two, in a way, exercise quizzes. So these are not graded actually. So that's the first one is testing how to enter info into Stack, and the second one is the dump homework. So in the second one, you're just going to see how the homework grading actually works, right? This is something that you can use to test it. The first one, you can actually, I think I'm going to preview it. You can actually see how we can enter data in here, right? So there are some instructions in here. Just make sure you go over this, and you also try some of the alternatives in here, right? For example, for writing subscripts, there are two different ways. Just check each one and see if it works or not. All right, this is just for testing purposes. Okay, just keep this in mind. Okay, let's see. What else? I don't know if you have any question. Yeah, there's one thing, sorry. On this Thursday, which is the October 28th, for some reason, the 28th of October is given as a half day. I don't know. It's basically the afternoon should be actually off, but I usually don't. I don't want to actually spend 2 hours on some unnecessary things. So as a result, I'm going to do the 2-hour classes as usual, all right? So I'm going to assume that the vacation starts at 2 o'clock or something like that. All right, just keep this in mind. So I'm just going to do that 2 hours, because otherwise we won't have much time for the second chapter material, because I'm going to actually explain the dot and the cross products of vectors today, right? So in any case, I'll just start with this, but just keep in mind that there are notes that I have already written down, so you can go there and look at them. There are also material in your textbooks, but they are placed at different chapters. Just go to the appropriate chapter and look at them. So basically, we are going to define, first, let's remember that we have defined 2 operations for vectors: multiplication with a scalar and addition. We have defined by basically using the geometrical view of the vectors, right? Basically, this view is that expresses the vector as some quantity with a magnitude and a direction, right? But together with these operations, then we can express the vectors in an algebraic way. Algebra is the things like, I don't know, the multiplication, addition, and things like that, right? So there's something called vector algebra. So you can multiply vectors with numbers, you can add vectors. By using these 2 algebraic operations, I can express any vector in terms of some given standard unit vector. So for this, of course, I need a reference frame. I need some x, y, z axis, so that I should have already defined these 3 special unit vectors, the coordinate unit vectors, okay? But by using these, I can express any vector. So let's just remember that this is unit vector notation. So sometimes I'm going to ask you to specifically express a vector in unit vector notation. So if I say that, that's basically what I mean. Okay, I can also do everything in terms of this algebraic point of view as well. So both has some advantages, right? So in a given problem, you may want to use one of them instead of the other one, but that's basically specific to each problem. So as a result, just keep in mind of these two pictures in here. Sometimes by using one method, we can actually get information about the other one, whatever. Okay, so I'm going to define the products, vector products, basically the product of two vectors with each other. I'm going to define them with the geometrical view, but later we are going to see that it can be expressed in a nice way by using the algebraic view as well. But I'm just going to do the first definition in here. So let's say the products of a vector with a vector, right? Product of two vectors. Yeah, product of two vectors with each other. Let's say it like this. There are two, it is possible that you can define two different kinds of products. So one of them is called the, let me show it like that. It's called a dot product or a scalar product. The result is a scalar number. It's a number, right? Which can be positive or negative. So this is called a dot product because we show this with a dot. Sometimes people call this as a scalar product because the result is a scalar, right? So that's the first kind. The second kind is a product that we show with a cross sign, and the result is a vector. So we call this as a cross product. That's the name that I'm going to use because we show it with a cross sign, or sometimes people call this as the vector product because the result is a vector, right? So some people use these names interchangeably. Still in the literature, there are some other names. So for example, in a broader context, this product is actually called an inner product. And some people call these as outer products, right? But I mean, this is something that we don't need to know right now. So I'm just going to call them as a dot product and cross product. Just keep this in mind, okay? Since there are these two different kinds and they actually produce different things, it is important to distinguish the type of the product by using the correct sign. So as a result, writing these kind of expressions, all right, this is nonsense, right? I mean, you shouldn't do these because it's not apparent what kind of product we are taking in here, right? Is it a dot product or a cross product? You have to show some kind of a sign in here so that we can understand what kind of a product it is. Okay, just keep this in mind. Don't use any kind of annotation like that. I'm also telling you this because you are going to need this in the future, right? So I'm going to start describing the scalar product because this is easier. So what's the meaning of all of this? The only thing that I can say is that this is going to be useful, all right? This is going to be useful. In physics, we use both kinds of products a lot. So we will start both products in the mechanics part. So we will first see the dot product in work concept. We are going to see the cross product in when we see the torque concept or the angular momentum concept, all right? We'll first start with the angular momentum, okay? So it appears that these are extremely useful and it has been used in many different places. In what context, I cannot say because I mean, we have to go there and see the application, but usually this is the thing that you should notice. So whenever, I mean, some quantity depends on two vectors, for example, and the quantity is a vector quantity. For example, work is actually is dependent on a force and a displacement concept, but both force and displacement are vectors, but the work is a scalar. So it appears that this dot product is used. Otherwise, if the result is a vector, the cross product is used, right? You can also think of it like that. They have some geometrical meanings. So today I'll just talk about this geometrical meaning only, all right? Okay, so I'll start with the dot product. So I'll start with the definition, right? So we will have like these two vectors. So let's say dot product. Okay, so we have these two vectors, let's say A and B. Okay, so what's the dot product? In that case, what we do is we just move the vectors in such a way that they start from the same point. Okay. For the cross product as well, we make sure that they start from the same point. Okay. So as a result, they have the common toe, let's say, and we just use compute this angle between them. So let's say theta is the angle between the vectors. Okay, this is a number between 0 and 180 degrees. It can be 0. It can be 0 if the vectors are parallel. It can be 180 degrees if they are anti-parallel, right? I mean, we have this range in here, but usually we don't take this angle to be bigger than 180 degrees or smaller than 0, right? Usually like that. Okay. So in any case, so that's the definition in here. So A dot B, we said that it's just a scalar. It appears that this is for the length of the vectors. I don't want to put an extra vector sign inside so that it is kind of easier to read, right? So as a result, I'm going to show the length of the vector A like that, length of vector B, and the cosine of the angle between them. Okay, so let's not question anything. Let's just take this. I mean, this is the definition then. Okay, what's the meaning? Again, we are going to see that it's going to be useful, right? But there is this other way of actually looking at it. This A times cosine theta, for example, I can think of it as the component of A along some direction. So let's just draw the same picture again. So this time, I think let me just draw it like that. Okay, this is A, this is B, okay? So if you remember what we have said about the components, so this is the vector A. If we just take its perpendicular projection on the direction of the vector B, there's some kind of a segment in here. We call the scalar segment in here the component. So I'm just going to show it in here as with this notation. So that's the component of A along the direction of B. Direction of B, right? The magnitude of B is not relevant in here. We're talking about the components, right? So in terms of this angle theta, in terms of that angle theta, I can write down this component as the length of the vector A multiplied with the cosine of the angle, right? So the cosine somehow enters because of that. It's the factor that we use to find the components. And for that reason, I can write down the dot product as, okay, I mean, this is just a view. You can actually think of it like the component of A multiplied with the length of B, all right? So in a way, you're taking some direction in space, and that direction is the direction parallel to B. And you're just multiplying the components of both vectors along that direction. But why direction of B? I don't know. Is it a coincidence? No, it is not. But when we see the other formulas, you're going to see that this is actually kind of makes sense. But in any case, let me keep explaining this, right? Again, let me state what is happening in here. So I just take some direction in here, some certain direction. I know that the component of B along that direction is its length. And I know that the component of A along that direction is this number in here. It is length of A multiplied with cosine theta. It is this one. Essentially, I'm multiplying the components of both vectors along that direction, right? This is the thing that I have done. But can I do the same calculation for some other direction? Like, for example, this one along this direction, for example. Can I take the components of both vectors along that direction and then multiply them? Can I get the same value? And the answer is yes. So let me first erase this. Let me correct this. Okay, so along that direction, so let me draw this picture again. So this is A, sorry. This is A. What is A? This is A, all right? This is B. The same vectors again, this time. However, I'm taking the projection of B along the direction pointed out by A, so that direction. So this is the component of B along A. So let's write this thing down. Component of B, component of the vector B along the direction of A, okay? I'm using this subscript notation for components, all right? So this is also given as B times cosine theta. And so as a result, in this formula, then I can see that this is the component of B along that direction. And so whatever, so therefore A dot B can also be considered as the length of A multiplied with the component of B along A. Right? This is just an alternative view, sorry. So if I take this direction in here, B has a component given by this expression. A has a component given by this expression. So therefore, I'm essentially taking the product of these two components. So the next question might be like, for example, if I take my direction like that, can I still express the dot product as the product of the components of A and B? A and B. But this time, I mean, these vectors have some non-zero components along some other direction. So as a result, let's just postpone this question to a later point. But when we see this unit vector notation, this is kind of more or less what we do. How can a component be of a vector be a scalar? Well, we have defined it to be a scalar. Okay, I mean, that's specifically something that I have stressed on. I define the component to be the scalar number, right? It's just a number. It's a signed number, right? It can be positive, negative, or zero. But it's a scalar, okay? So, I mean, the reason why I'm doing this, I define it like that because of these things like that, right? The X component, for example, I want this to be a number. So I want this thing to be a number. I want this thing to be a number. So as a result, I define the component to be a number, right? So some people may define components to be vectors, but they are completely useless as a concept, right? You can define anything to be anything, actually. That's up to you. But a component which is a vector is a completely useless concept. You have to define it as a number. Only in those cases, these kind of things become useful. Okay, let's state it like this. In any case, so that's our definition. But when I look at this primary definition, I can also think of it like that, all right? I can also think of it like this. Why do I do this? Because of some useful thing. I mean, this is something that I have stressed on this. So think about it like this. So let's say that we have a vector equation in here. By using this equation, we can claim that their components are also satisfy the same equation. Sorry, I stated in the most incorrect way. So we have some vector addition expression, right? let's say C is a sum of A and B vectors. So A is a vector like that, and B is a vector like this, and C is just a vector sum of these two, A and B. And let's say that X is a direction like this, right? X is this direction. So in that case, A sub X is this component, this number in here, right? So this is A sub X. This is B sub X, right? Even when they are signed, you can see that this is true. So see, this component is equal to sum of these two, okay? So, I mean, this doesn't have to be just the Cartesian component. So this can be any direction, actually. And in that case, I mean, if the vectors are added up, the components are also added up. So I can actually replace this with any components, okay? So as a result, I think I'm going to do it like this. Sorry about that. So suppose that I have some thing like this. Yeah, I would like to do it like that, all right? So I'm basically considering the dot product of, let's say, yeah, I would like to see the dot product of A plus B with some vector D. Okay. Think of it like this, right? So in that case, I'm going to erase this picture in here, right? Why do I erase it? So yeah, don't erase it, sorry. Let's just leave it there, right? So A is a vector like that, but I'm going to draw the same picture. B is a vector like that. And let's say that D is a vector like this. Let me draw it like that with a blue color perhaps. D is a vector like this. And I'm taking the dot product of A plus B this time with D. But you can see that, I mean, I can think of this A plus B as this vector in here. I have to take the component of that vector and multiply it with the length of D. And yeah, let me just say it like this. So this is basically, I mean, if I call this as C, sorry about this, I made a horrible mistake in here, right? So in any case, this is basically the component of this vector along the direction D multiplied with the length of D. And I can write this thing down as the sum of the components of A and B along the same direction. And because of that, I can therefore see that this can be expressed like that. But therefore, this is like the, yeah, it's something like this, right? I'm just going to cut the story short. But eventually, I just then deduce that I can basically distribute this dot product over the addition, right? That's basically what I wanted to say. All right. So the conclusion is simple, but the explanation is horrible. All right. So, I mean, just like we expect from a product, the dot product satisfies distributivity. So that's the distributivity. Okay. So the dot product is distributive over the addition. The order is unimportant. I can also have the same kind of distributivity on the if the addition appears on the other side. It doesn't matter, right? So that's D dot A plus D dot B. Okay, so this tells you that the dot product satisfies this basic property of that you would expect from products. And I mean, this is therefore something that tells you that you can use the vector algebra to do this dot product calculation easily, because in that case, in the algebra, you're using the products and the addition, summation, and things like that. And so as a result, this is consistent with this algebraic sensing here, right? as a result, this is kind of an important result. Another thing in here is the symmetry. D dot A is the same thing as A dot D, right? The value of the product doesn't depend on in which order you have taken the products. So that's kind of obvious. So that's called the commutativity. When you take quantum mechanics, you are going to learn this word a lot. So there will be situations where things do commute or they don't commute or whatever. So basically, when we say commutativity, it's just it says that in a product, I can change the places of these two symbols. Right? So these are our basic rules of algebra. And then there are these other rules. I'm just going to talk about this. So first, there are these three situations that I need to distinguish for the orientation, relative orientation of two vectors. This angle might be less than 90 degrees. That angle might be 90 degrees. Theta is equal to 90 degrees. And the other situation, theta is bigger than 90 degrees. Okay, there are these three special cases of interest. These are kind of important. So we can see that A dot B is the product of the lengths of these vectors. Lengths are always positive, multiplied with cosine theta, and cosine theta has a different sign for different angles. So as a result, we basically distinguish these three cases. So we can see that in this situation, for example, the dot product is positive. Right? Let me just say it like this. So this is the situation where A dot B is positive. Okay. All right. So because the cosine of the angle is basically a positive number for the situation between 0 and 90 degrees. 0 is included in here. At theta equals 90 degrees, cosine theta is 0. Cosine of 90 degrees is 0. So therefore, A dot B is equal to 0. When the vectors are perpendicular to each other, their dot product is 0. On the other hand, when theta is bigger than 90 degrees, in that case, the cosine is negative. So in that case, A dot B is negative. Okay, so that's actually a very nice property. So by just looking at the sign of the dot product, I can see if the angle between these two vectors is actually less than 90 degrees or bigger than 90 degrees. Okay, I mean, by just looking at the sign, by looking at the value, we can also determine what the angle is, but this is at least qualitatively important conclusion. But this is especially very important when they are perpendicular to each other, that the dot product is 0. So therefore, this is the place where this thing changes sign. So that's basically, you can think of it as a way to determine if two vectors are perpendicular to each other. So let's say it like this. So this is a way to determine if two vectors are perpendicular to each other. Right? Compute their dot product and see if it's equal to 0. So you can do this dot product either geometrically or algebraically. So there are different kinds of situations where this is quite useful. This can happen in real life, actually. So as a result, I mean, this is very useful, actually, right? Let me just say it like this, but let's just look at it from the component point of view. So in this case, for example, A has a positive component along B. A has a positive component. In this situation, the component of A along B is equal to 0 because of this perpendicularity in here. And in this case, A has a negative component along B. So this the component is a negative number. So this is the dot product also gives us in a way, gives us a sign of the component of one of the vectors with respect to the direction of the other one. We can also think of it like that. Okay. The result is scalar. So what the sign means? Well, scalar is just a real number, right? Sign means this. I mean, a scalar number has a sign. We have talked about this before, actually. We said that the temperature is a scalar. It doesn't represent any direction in space. So, I mean, scalar quantities can be negative as well. No problem with this. There are some very special scalar quantities which are always positive, but this doesn't mean anything, right? Like mass has to be always positive, but I mean, there are situations where some people imagine negative masses as well. I mean, this doesn't actually mean anything much, but there are some certain things like, I don't know, some certain things are always positive, doesn't actually mean anything about them. So when we say scalar, we don't say a quantity which is always positive. No, that's not the case. When we say a scalar, scalar means it can be expressed by a number only, but that number can be negative as well, right? Okay, so next thing, can you scroll up a little? Why? I have talked about distributivity, commutativity. But yeah, I'm just going to go ahead, all right? So there is this situation where theta is equal to 0. Why is it special? I don't know. It's not just special. I mean, we have these two parallel vectors. So A dot B is, I mean, theta is 0, so the cosine of the that angle is equal to 1. So the dot product is equal to just the product of the lengths. So, I don't know. But there's a very special case when these two vectors are the same. So I think I'm going to write this thing down as a relationship. So the length of the dot product of a vector with itself is equal to length squared. And so this is the relationship, or I can basically write the length of the vector as the square root of the dot product of itself, right? Okay, I think you can see the screen, so you can also see all my messages. All right. Why is this important? I think I'm going to prove the Pythagorean theorem from this. But in any case, let's just pass to the algebraic picture. So to actually pass to the algebraic picture, I have to talk about the dot products of Cartesian unit vectors. Right, this is I, J, K. So I don't need to say much. In a reference frame, we always choose X, Y, and the Z axes to be perpendicular to each other. Right? So therefore, these unit vectors are perpendicular to each other. I, J, K. So these are unit vectors along these three special directions. Okay. We have defined them earlier. First, they are perpendicular to each other. So that means the dot product of I with J is equal to 0, as the dot product of J with I, and the dot product of I with K is equal to 0, and J with K is equal to 0, right? Let me say, etc. Right? all of these unit vectors are perpendicular to each other. And because of the rule that the dot product of two perpendicular vectors is equal to 0, because of this rule, we can easily say that the dot product of different unit vectors is equal to 0. Let's say it like, yeah, let me say it like that, right? Dot products of different unit vectors among this set, all right? Let's say gives 0. And then we talk about the dot product of a unit vector with itself. This gives 1 then. So let's then talk about this. So I dot I, that's equal to 1. Why? Because I'm using this rule now. So it's the dot product of itself with itself. So it's going to give the length squared, but the length is equal to 1. So therefore, j dot j is equal to 1. K dot k is equal to 1. Okay. So as a result, I mean, you can easily see what the dot products of these unit vectors are. The result is a scalar, it's a number, so it's either 0 or 1. And well, you can easily see in which case it is 1. And in which case it is 0. You just look at the directions. Okay, so how do I pass from this to the unit vector notation? So let's say that we have these two vectors, A and B. Let's say that they are written in unit vector notation. Okay, sorry about this. I'm just going to spend such time to write all the components in here, but I'm writing this symbolically in here. So suppose I have these vectors and I have written them in unit vector notation. Okay. Right. B, Y, J, and B, Z, K, right? So what I want to do is to take the dot product of these two vectors by using this their unit vector expressions, okay? Now, the nice thing in here is the distributivity. So as a result, they're like the 3 terms multiplied with 3 terms. So I can express this as the sum of these 9 different products. So let me just write it down like that. So we have AX, BX, I dot I. I'm not going to write everything down. I'm just going to give you the idea, all right? AX, BY, I dot J. And let me say dot, 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 right? Right? I don't want to write everything because most of them will be 0, but you can actually kind of see what's happening in here. So in each term, we have a dot product of one of these Cartesian unit vectors with another Cartesian unit vector. So in some terms, we take the dot product of a unit vector with itself. In some other terms, we have the dot product of 2 different unit vectors. If these unit vectors are different, then the result is 0, in which case I don't need to write them down. If they are same, then the result is 1, in which case we don't need to write down 1 because 1 is 1. 1 multiplied with 1, the other things gives us the nice thing. So, right, there are actually 9 terms in here. You can see that 6 of these terms actually go away because of this 0 dot product. There are only 3 terms which survive. So that therefore, A dot B can be expressed as the product of the X components of these 2 vectors plus the products of the Y components plus products of the Z components. All right. That's actually one of the nicest expressions Because, I mean, you can see that the unit vector notation is actually quite useful, extremely useful also for computing the dot product of two vectors. Because by just using the components, I'm just going to multiply some components with each other and add them up, and I can express the dot product. Okay, then that means that I have like these two alternative ways of computing the dot product of two vectors. I can use this geometric picture, all right, in terms of cosine theta and things like that. Or I can use this algebraic picture, right? Let me go back to the beginning. I think I'm going to use this. I said that there's a geometrical view of actually viewing the vectors as arrows pointed in space, and there's an algebraic view, right? Now, I have defined the dot product with the geometrical view by this thing in here, by using their magnitudes and the angles between them and things like that. Now we have a second way of actually computing the dot product by using this unit vector notation. In that case, I don't know anything about the magnitude or the angles between them and whatever, but that's an alternative way of actually computing these. Okay. What is nice in here is that, let me go to the very end. I mean, I need a reference frame to be able to define these X, Y, and Z components, right? I should have defined an X, Y, or Z component, Z axes. However, usually this reference frame, X, Y, Z frame, depends on the choice of the person. So I can choose my X, Y, Z frame like this. Somebody else chooses a different X, Y, Z frame. In which case, that other person is going to express the same vectors with different components, right? But even when they use these different components, they are going to actually, by using this formula again, they are going to compute the same dot product again, okay? So as a result, even though these components depend on the frame that you choose, it is dependent on choice, but the final result is independent of your choice of the reference frame. All right, that's somewhat important, but in any case, let's just say, I don't know, for example, A, B. I mean, this is something that I have said at the beginning. So if I choose my x-axis, for example, along the direction of B and the y-axis like that, in which case, AX is basically the component of A along B. There's a Y component of A, I don't know, it's something else. B has an X component, which is the length of B, but it has a Y component, which is 0, right? So as a result, if I just compute the respective components, the Y component of A is multiplied with the Y component of B, but that doesn't produce anything because this is 0. So as a result, in that case, I get A dot B is equal to the component of A along the X direction multiplied with the length of B, right? So we then deduce what I have said about the previously, right? A dot B is basically the products of the components along a given direction, but this is true provided only if one of the vectors have 0 components in other directions. If not, then that's the expression in here. So basically, you just take the products of components in all possible directions and add them up. You can then think of it as an alternative way of defining the dot product. Okay, so in any case, I'm not done, but I need to give a break in here. Yes. Yeah, that's an appropriate time to give a break. I think I need one more relationship. It's the Pythagorean theorem, essentially. I need one more relationship that I need to state, and probably I need to solve a problem about this to show that this is actually some useful geometrical thing. I mean, it's a useful thing to solve some geometrical problems, but I don't know. Let's see. Let's see if I can come up with a problem. Right, let me stop the recording.